Alright, so the first thing that I want you to understand is when we are doing rigid simulation in Vellum, we are using Vellum grains to represent our original object, and then these Vellum grains will be behaving as rigid bodies in our simulation. Okay, so there are 3 steps to this. First is we are taking an object, it can be anything, it can be a chair, a table, or a box, and then we are filling these object with Vellum grains. Okay, now that we have filled our object with vellum grains, these vellum grains will behave as one object. They will be behaving as one single entity, and they will be simulating as rigid bodies. Okay, thus representing our original object, and then later on we'll be able to transform our original object onto these vellum grains. Okay, so this is the basic concept. Now let's move on to our main tutorial. So let's get started. We will start with our geometry network. Okay, I'll just rename it, I'll call it sim, and as always I'll change the color as well. We can dive inside and let's just show you an example first. Okay, so what I'm going to do is I'll just create a box here. Okay, this is our box. Let's assume that we want this box to behave as a rigid body. Okay, so I'll just move it up and something like this. I'll move it up in y direction, and if it is a rigid body, this will fall down, and it will basically behave as a box, a rigid box. Okay, so how we can do that in Vellum is by creating a Vellum configure grain pieces. Okay, there are 2 options: Vellum configure grain and Vellum configure grain pieces. We'll choose the second one, Vellum configure grain pieces. And with this node, what we are going to do, we are going to get 2 constants. One is Vellum grain. This is our grains. These are our grains, which are filling our object. Okay. And the second one is shape match. So this tries to keep the shape of the object intact. Okay. This is the constant that we are going to use. So these are the 2 constants, and let's connect it to a Vellum solver, and not this. Connect constants to constants. I'll just turn on ground floor. Let me turn it on, and now if we run this, if I run this simulation, you will see that these grains will be behaving as rigid body. Okay, and they are basically representing our box. They are falling down, and the grains are sticking together, and they are keeping the shape which it originally had, something like this. But as you can see, our box is quite bigger than our grains, so we have some settings here that we can use to fix this. We want all this box to be filled with grains. Okay, so let me just decrease the particle size to 0.25. What this will do is it will create decrease the size of the particle, and what I can do is I come to max spheres, increase the number of spheres here, maybe something like 2000, and this is what we are getting. Okay, not perfect, but we are there. So let me just run this now, and let's see what we are getting. And as you can see, if I go back, this grains are behaving as one rigid body, one rigid object. Okay, we can obviously come here, and what we want is we want this box to be filled with grains. So I'll just come to maximum radius scale, and this decides what would be the maximum radius of a sphere here, of a grain here. Okay, so I'm increasing it to 4.49, and another thing that I can do is maybe I can increase the number of spheres here to maybe something like 2500. So this is what we are getting. We have spheres of different sizes here, variable sizes, as we have turned on our maximum sphere scale. But you can see that nothing is happening here. In fact, we are getting an error. So what's happening here is that we need to come to, let me just reset it. Okay, and as you can see, it is not running. In fact, we are getting an error. Come to the advanced, and here come to OpenCL and turn this off. OpenCL neighbor scratch search, and you can see that this is working perfectly now. Okay, so we have to turn this off when we are using variable scale for our spheres. As you can see, I have turned on the maximum radius scale, and the maximum radius scale is 4.49. If I turn this off and if I turn this on, now you can see that it would be working fine. Okay, but it is necessary when you turn on the maximum radius scale, just make sure that the OpenCL neighbor search is turned off, otherwise it won't work. So let me just turn off, and now we can see that this is basically working. So this box is behaving just like a rigid body. Okay, what I can do here is, let me just create a Vellum, where is it, Vellum transform pieces. Okay, so now what we want is, we want to transform all these grains to our original object, which is the box here. Okay, if I do this, let me see. As you can see, all these pieces, they are representing the box here, and our rigid body simulation is basically transferred to our main box. If I just rotate this box a bit, and now if I run the simulation again, you'll be able to see the proper simulation here, something like this. Okay, so this is the basic thing that I told you earlier also. We are using an object, we are filling it with the grains, and those grains are sticking together, they are behaving as one object, and thus behaving as rigid body. And then those transformation, those rigid transformation that we are achieving in simulation, we are transforming that to a main box or main object with the help of transform pieces. I am going to make some copies here, so I'm using a copy and transform node. Let me just connect it to our box, and I'll just move it up. So as you can see, we have 2 copies of the box, and if I connect it to our grains, you can see we are now getting 2 boxes. All right, and if you come to shape match, you can see everything is okay. You don't need to really change anything in the shape match here. The shape match just make sure that we are, just make sure that we are getting the same, the rigid body shape is being intact. So as you can see here, when we are running the simulation by 2 objects, they are colliding with each other, they are going inside each other. So if I increase the substeps, as I did here, I have increased the substeps to 2, and that worked fine. But when we are using the transform pieces, when we are transforming the simulation here, we are not getting anything, and that is because we need to have an identification attribute on these boxes here. So what is happening here is, when we are just using one object or one box, and then we create grains or a grain cluster to represent that box for Vellum rigids, we can easily identify that this grain cluster represents this box. Okay, so we can, after the simulation, we can easily replace those grain clusters with that box. But when we have multiple objects or multiple boxes here, then we will be creating multiple grain clusters. Okay, and after the simulation, it will be very confusing for the Vellum simulation or Houdini, that which grain cluster belongs to which object, which grain cluster we have to replace with which object or which box. Okay, and that is why we need to have a specific piece attribute or a identification attribute, so that our Vellum transform pieces know that this specific grain cluster will represent this specific object or box, and we have to replace that grain cluster with this box. Okay, so that is why we need to use a piece attribute here. Okay, so as you can see that the Vellum transform pieces is confused here because we have multiple objects or multiple boxes. It is confused at which grain cluster represent which box, and that is why we have to use a piece attribute here. As you can see, we have used a copy to transform, and there are 2 boxes here. Okay, so by default, the Vellum grains is creating a piece attribute here to identify which grain belong to which cluster. Okay, so we have two boxes here, and when we are using the Vellum grain constant, we are creating two grain clusters here, and we are creating a piece attribute here from connectivity, so that we know which grain piece belong to which cluster. Okay, so we have this piece attribute, as you can see, and if I just use a marker here instead of color, you can see that all the grains below has a piece attribute of 0 and all the grains above has a piece attribute of 1, so that they know which cluster they belong to. If we come to Vellum shape match, we are using the piece attribute here as well to define the pieces. Okay, if you come to the Vellum grains here, you'll be seeing that we are creating that piece attribute from connectivity. Okay, so when we are connecting our objects, in this case two boxes, into our Vellum grains, the Vellum grains is giving those two objects a piece attribute, okay, with the help of a connectivity node. So when we are transforming those boxes into grains, those grains are also inheriting those piece attributes. Okay, but there's a problem here. When we finally want to use a Vellum transform pieces to replace our grains with our boxes, we will not be able to do that because our original boxes do not have any piece attribute. Okay, so that is why we need to create a piece attribute on the boxes. So let's change the define pieces from attribute here. Okay, and nothing is happening here. As I said, because the boxes do not have any piece attribute, the grains are not inheriting any piece attribute, and that's why the whole simulation has gone to 0. Nothing is happening here. Okay, we need to create a piece attribute here for our objects. So if I change it back to from connectivity, as you can see, the boxes are given piece attribute, and so the grains are also inheriting that, and now the simulation is working fine. But if I change it back to from attribute, we do not have any piece attribute here. We need to give piece attribute to our boxes. That is what the main concern is. We have two boxes and we need to give them piece attribute or some kind of identification attribute. So let's just turn the copy number attribute here, okay, in the our copy to transform node. After that, what I'm going to do is I'll just create a attribute triangle, and with the help of that copy number attribute, we'll create a piece attribute. Okay, but as you can see, this piece attribute is primitive. So what we are going to do is we will be creating a attribute promote here, attribute promote node, so that we will be able to promote this attribute, this primitive attribute, to point attribute copy num. The copy num attribute is now being promoted to a point attribute. It is a point attribute now, and now we will be able to create a piece attribute with our attribute triangle here. Okay, so this is a copy num attribute, which is a point attribute. If I just visualize this and if I change it to marker, you can see that the first box has a value 0 and the box above has a value of 1. So what I'm going to do is I'll just create @piece in the attribute triangle is going to be equal to @copy num attribute. Okay, what I'm going to do is I'm getting some error, and this is copy num, so let me just convert it into an integer. So int, and let's put the copy num attribute into a bracket. So now we have a piece attribute which is equal to our copy num attribute, and now everything is working fine. As you can see, all the grains are inheriting the piece attribute. Okay, and come to Vellum grain. As you can see, we are using define pieces from attribute, so we have a piece attribute on our boxes which is being inherited by our grains, and now when we run this simulation, it will work fine. So these boxes are behaving just like rigid boxes, okay, rigid bodies, and that's what we wanted. If I change the number to maybe 10, actually no, maybe 5 would be a good example. Let's just go back to frame 1. As you can see, now there are 5 boxes here, and let me just give them random rotation. So I'm just rotating them, and this is what we are getting now. Okay, if I run the simulation now, as you can see, we are getting 5 boxes here which are getting a rigid body simulation inside a Vellum simulation, okay, with the help of our Vellum grains. Those Vellum grains are behaving, those Vellum grain clusters are behaving as one object, and then they are representing the boxes. And now if I use the Vellum transform pieces, we will be able to replace them. But we are still getting problems here, and I think this must be a bug. We have boxes here, and I think, why is it not working? There must be some issue here. Let me just move it here. Is it because of the output? No, that is fine. This is also fine. If I reset this viewport, okay, so there's actually some mistake here. Okay, we are using our original boxes without the piece attribute for our final transformation. We need to connect the boxes here. Okay, and now you can see when we have connected the proper inputs in our Vellum transform pieces, we are getting the final results, the correct results here. 4 boxes being represented by Vellum grain clusters inside a Vellum simulation behaving as a rigid body. And then finally, we are replacing them with our boxes. So this is what we are getting. I think if we close this, I just want to show you an example and make it back to connectivity. You will see that these boxes will behave as rigid bodies, okay, because we are giving them a piece attribute with the help of a connectivity. But this is working fine, but we will not be able to transform them, okay, because our original boxes do not have the piece attribute, and that's why we have created this piece attribute on our boxes here. Okay, so let me just come back to frame 1, and maybe I'll just turn it back like this and like this. Let's turn it on, let's turn it back on, and if I just run this, you can see that this is working fine. All these boxes are being represented by our grains here, something like this. And let me just increase the maximum spheres to 5000 here, so that we have enough amount of spheres or grains for our boxes. And if I increase the maximum radius scale here, you will see that the size of the spheres have also increased. Okay, so this is looking fine. Maybe I can change the particle size also to 0.15, and now this is what we are getting. Just make sure that the grain clusters or the grains that are representing the object are as close to the original object as possible, okay, which they are representing. So if I come back here and run the simulation, this is working perfectly fine. There may be some issues here because we are using low substeps here. They colliding with each other in a way that they are intersecting each other, and that's not what we want. But let's compare these Vellum rigids with our actual RBD simulation. Okay, so if I come here to this copy and transform node, we have 4 or 5 boxes here, and if I use a RBD configure, this will prepare these boxes for a RBD simulation. And if I create a RBD bullet solver and connect all these constants and all these proxy and main geometries, and go to our collisions and turn on our ground plane, and if I go back to frame 1, if I play this, you can see this is our RBD bullet solver. Okay, the main rigid body simulator inside of a Houdini, and this is our Vellum simulator. If I compare this, let's merge them. Let's first use a transform, move it in the Z direction, somewhere like this. And if I merge both of them, and if we play both of them and see, they may look quite similar to each other actually. So this is On the right side we have our rigid simulation, and on the left side we have our Vellum rigid simulation. And this is what we are getting. Both of the rigid body simulation is actually looking quite nice. The only thing is that the Vellum rigid simulation on the left can actually interact with other Vellum objects, like a cloth or a Vellum liquid or anything else, a balloon maybe. Okay, and that's what we will be doing in our tutorial next. So let's move on. So this was that. The only thing is, the only difference between the rigids and the Vellum rigids is that the rigid simulation in Vellum, which we are doing with the help of our Vellum grains, can actually participate with other Vellum elements like balloons or cloth or Vellum fluid. Okay, but the rigid body simulation, the RBD simulation, which is the main RBD simulation inside of a Houdini, cannot do that, does not interact with other Vellum simulations or other smoke or anything else. Okay, so that's what the main difference here is. The Vellum rigids is very good in small scale simulations, when we are doing small scale rigid simulations, which also includes other Vellum elements, then this is perfect. If you are just doing regular rigid body simulation, then obviously the main rigid body simulator inside Houdini, the RBD simulator, the RBD simulation is going to be far superior and will give you far more accurate and easier results actually. So that is that. Okay, so let's move on. I'll just go outside, and this is sim, so I'll just rename it to sim2, or actually maybe I'll just rename it to example. So I hope you understand that Vellum rigids example that I showed you, the Vellum rigids that we created with the help of our grains. I'm just creating a new geometry network here. Let's call it sim, and we will dive inside here. We will move on to our actual tutorial here. Okay, so the first thing that I'm going to do now is I'll just create a file here, and I'll bring in our table or chair, our object here. Okay, so we have our chair here, and this is an alembic, so I'll just unpack this. Make sure to unpack it, use a unpack node, and we have our unpack chair here. Okay, which is looking actually quite nice. Are there any transfer attributes to transfer? No. So what next? We will just use a convert node. Let me just bring it out. Convert node, convert, and I forgot to transfer the groups here, so that, and this is actually not a convert node. I made a mistake here. So use a convert node, convert, convert, yes, just to make sure that everything here is a polygon. Okay, let me just check, and yeah, everything looks good. What we can do next is we are going to create Vellum grains on this chair. Okay, the grain which will then represent this chair as which will represent this chair in a Vellum simulation. So let's create a Vellum grain configure from pieces, and here we are getting our two constraints, shape match and the Vellum grains. Okay, but we need to do a lot of work here. Okay, so let's come to our Vellum grains, increase the maximum spheres to 3000. I'll come to particle size and decrease the particle size to 0.015, something like this. So our whole chair has enough amount of grains here. Okay, what I can do is I'll just turn on the maximum radius scale here. Okay, and let me just increase the size to something like 6, and the chair is filled with grains now. Just this portion is looking quite different, so come to Vellum grains and let's fix this. What I can do is maybe I'll increase the number of particles to number of spheres to 5000, but nothing is happening here. Let's increase the ISO value to maybe 0.054 or maybe 0.01, and now you can see that that portion is also filled with grains, and these grains will represent our chair. But as I template our original chair, you can see that these grains are actually overflowing our main object. So let's just decrease the size of the ISO 0.05005, and this is actually looking quite nice. So these grains can actually represent our chair now. Okay, I'll come to Vellum shape match and I can see they are interconnected. I'll just create a transform node here just to make sure that this chair is moved up so that we can do our test simulation. This is moved in the y direction, and after the Vellum shape match, I'm just going to connect it to our Vellum solver. Something like this. And let's just turn on our ground plane, and if I play this, nothing is happening because we need to go to our advanced section, come to OpenCL and turn off our OpenCL neighbor siege. And now when we run this, you can see there's a problem here. All different parts of our chair are given a different piece attribute, and because of that, they are separating from each other when the simulation actually starts. Okay, so there actually are 7 elements because we are using defined pieces from connectivity. Okay, so all these different pieces are given a piece attribute, and because of that piece attribute, they are behaving as different pieces, not as one piece. How can we fix that? As I showed you in our earlier example, what we can do is, let me just move it down. I'm going to create a attribute triangle here. Oh, by mistake I moved in. So this is our attribute triangle. I'm going to create a piece attribute here just for this example, just for this moment. So I@piece is not in the capital. I@piece in small letters is going to be equal to 0. Okay, so this whole chair has a piece attribute of 0, which means that all these pieces should be connected and should behave as one object. But as you can see, we have connectivity here, and in the Vellum shape match we have attribute. So come back to our Vellum grains constraint and change the defined pieces to from attribute. So these grains will inherit our piece attribute, and now you can see that as the piece attribute is 0 for all the grains, they are behaving as one object. But the only thing is here